Hello, Math 200 students. We are looking at Chapter 6 today. Chapter 6 is about confidence intervals for the mean, or confidence intervals for the standard deviation, confidence intervals in general. So when we are taking a sample, we get of some statistics. Let's say the weight of an average college student male. And we take a sample of 100 males that fit that category, and we get that mean. That does not mean that the mean of our sample is the mean of the entire population of male college students. So, in fact, it would be the probability that it would be zero. So what we do is we don't say that it was that is the true mean, but what we do is we build an interval around that, and we say the mean is almost certainly in that interval, and that's called a confidence interval. Okay, and the wider we make our interval, the higher our confidence is that the true mean of the population is inside of that interval. The more narrow our interval, the less confidence we have that the true mean is inside of that interval. All right, so that's just an introduction to this. Let's get on and read some of this chapter and take the concepts as they come. Estimating population parameters. In this chapter, you will learn an important technique of statistical inference. To use sample statistics to estimate the value of an unknown population parameter. In this section and the next, you will learn how to use sample statistics to make an estimate of the population parameter mu, which is the mean, when the population standard deviation sigma is known or when sigma is unknown. So 6.1 is how to construct a confidence interval for the mean when you know the population standard deviation somehow. 6.2 is how to construct the confidence interval for the mean when you don't even know that, when you don't know the population standard deviation at all. So, to make such an inference, begin by finding a point estimate. A point estimate is a single value estimate for a population parameter. The most unbiased point estimate of the population mean mu is the sample mean x bar. So it's kind of what I was saying before. So we get our mean of our sample of guys, and that's called x bar because it's not the true population mean, we call x bar the sample mean. The true population mean, Greek letter mu, is going to be estimated based on that sample mean x bar. X bar is our point estimate. It's the single value estimate for the population parameter. The validity of an estimation method is increased when you use a sample statistic that is unbiased and has low variability. So in other words, it's better to use a sample mean x bar than it would be just a guess. Like I might say, well, I would just guess that the population mean weight for all male college students would be 170 pounds. I don't know, something like that. But it would be better, I would get a much more unbiased estimate for the mean of the population by taking some sort of a sample and taking the mean of that sample. A statistic is unbiased if it does not overestimate or underestimate the population parameter. In Chapter 5, you learned that the mean of all possible sample means of the sample size equals the population mean. So in other words, if you take all possible samples, so not just one sample, but lots and lots and lots and lots of samples, and you take the mean of all the means of those samples, then you're going to get the population mean. As a result, x bar is an unbiased estimator of mu. When the standard error sigma over the square root of n of a sample mean is decreased by increasing n, it becomes less variable. So in other words, when you increase the size of our sample, n is the sample size, how many subjects we have in our sample, then there's less variability in our standard error of our sample mean. Example 1. An economics researcher is collecting data about grocery store employees in a county. The data listed below represents a random sample of the number of hours worked by 40 employees from several grocery stores in the county. Find a point estimate of the population mean mu. All we're going to do is find the mean of all this. And probably what I would suggest is that you would type all of these into the calculator into the list, L1. I'll just try to show you that. Remind you a reminder of how to do that. You just go to stat. Just hit stat, and you click edit, and that allows you to edit a list. So if you want to clear out what we got, go up to L2, hit clear, hit enter, and that'll clear out that whole list. So I'm gonna go up to L1, hit clear, and then hit enter, and that'll clear out the L1. And then I would just type all those numbers into L1. I would have the entire list of numbers in L1, and once I did that, I would go to stat. I would go to tests. Nope. I would go to calculate, and option 1 is one variable stats. That tells you the mean, the standard deviation, the lower quartile, upper quartile, median, all that good stuff. Range, I think it tells you that too. Can't remember. All right, so that would be how I would do that problem if I were you. If you want to, you could just add up all these numbers and divide by how many there are, and that would tell you the mean as well. But you might as well type them all in and do what I just said, because that's not only going to tell you the mean, it's going to tell you other things about that sample as well, which you might be asked later on. Next page. In example 1, the probability that the population mean is exactly 29.6 is virtually 0. So 29.6 was the mean of that sample. But as I said earlier, the probability that the population mean is exactly that is virtually 0. I'd say it is 0. It's 1 over infinity. So instead of estimating mu to be exactly 29.6 using a point estimate, you can estimate that mu lies in an interval. This is called making an interval estimate. An interval estimate is an interval or range of values used to estimate a population parameter. Although you can assume that the point estimate in example 1 is not equal to the actual population mean, it is probably very close to it. To form an interval estimate, use the point estimate as the center of the interval and then add and subtract a margin of error. For instance, if the margin of error is 2.1, then an interval estimate would be given by 29.6 plus or minus 2.1. So you're taking your point estimate to 29.6 and you are creating an interval around that point estimate. So you're adding 2.1 to it and you're subtracting 2.1 from it. And so you can say with some degree of confidence that the true population mean is between 27.5 and 31.7. The point estimate and interval estimate are shown in that figure, as we just said. Before finding a margin of error for an interval estimate, you should first determine how confident you need to be that your interval estimate contains the population mean, mu. The level of confidence, indicated by the letter C, is the probability that the interval estimate contains the population parameter, assuming that the estimation process is repeated a large number of times. You know from the central limit theorem that when n is greater than or equal to 30, the sampling distribution of sample means is a normal distribution. The level of confidence, C, is the area under the standard normal curve between the critical values negative z sub c and positive z sub c. Okay. Critical values are values that separate sample statistics that are probable from sample statistics that are improbable or unusual. You can see from the figure below that C is the percent of the area under the normal curve between those two values, those two critical values. The area remaining is 1 minus C, so the area in each tail, so the area here or the area here is half of that. So 1/2, 1 minus C. So let me just tell you, well, maybe it'll tell you. For instance, if C is 90%, that means 90% is in this blue area here. That means 10% is left to be divided up into these other two tails. So 5% would have to be here, and 5% would have to be here. All right, that's exactly what that is describing. All right, let's move on. The difference between the point estimate and the actual parameter value is called the sampling error. When mu is estimated, the sampling error is the difference x bar minus mu. In most cases, of course, mu is unknown and x bar varies from sample to sample. However, you can calculate a maximum value for the error when you know the level of confidence and the sampling distribution. Given a level of confidence C, the margin of error E, sometimes also called the maximum error of estimate or error tolerance, is the greatest possible distance between the point estimate and the value of the parameter it is estimating. For population mean mu, where sigma is known, the margin of error E equals z sub c times sigma of x bar, which equals z sub c times sigma over the square root of n. Right? Sigma sub x bar is the standard deviation of the of all of the samples, the distribution of sample means. So not just the sigma of a single sample, but the sigma of the distribution of sample means, which means you take the sigma and you divide it by the square root of n, where n is the sample size. When these conditions are met, the sample is random. So z sub c, when these conditions are met, the sample is random, at least one following is true, the population normally distributed, or n has to be greater than or equal to 30. So either, for this to work at all, the population has to be normally distributed, and then it doesn't matter what your sample size is. But if you're not sure whether the population is normally distributed, then you must have a sample size that is at least 30 in your sample. Z sub c comes from the standard normal distribution for a particular level of confidence. And you can get that in a table, but I can also show you how to get that on your calculator. All right, finding the margin of error. Use the data in example 1 in a 95% confidence interval to find the margin of error for the mean number of hours worked by grocery store employees. Assume the population standard deviation is 7.9 hours. All right, so we're going to follow this formula up here. All right, Z sub C, we're going to get that from our calculator. 95% confidence level. So here's what I do. I go to second distributions, and I go to inverse normal. Okay, and here's two ways you can do it. If we want a 95% confidence interval, that means what we're looking, we want 95% here in the middle. We want to get a confidence interval that is around this mean, but we want to find these values that will give me a 95% confidence interval, so that 95% of the area is between those two values. We're trying to find these values on the standard normal distribution that will accomplish that. All right, so one way you can do it is, again, do the inverse normal and do your area as 0.95. Since we're talking about a standard normal distribution, mu is going to be 0, sigma is going to be 1. That's true for a standard normal distribution. And you can do a center normal distribution. That means that you're trying to find 95%, the values where 95% of the data is between the two values. And then you go to paste. And you hit enter. And you see that the two values are negative 1.96 and positive 1.96, which is exactly what they have right here. Okay, another way to do it, and this is how some people with calculators that aren't the newest versions will have to do it this way. Only the newest versions allow you to do that center. All the older versions of the calculator only do a left tail. They won't do anything else but a left tail. So here's another way you could do it with a left tail. If 95% is here, that means 5% has to be divided between those two tails. So if 5% is divided into these two tails, that means how much is in each tail? That means 2.5%, because 2.5 is half of 5. 2.5% has to be in the left tail, and 2.5% has to be in the right tail. So you could also you do it this way. You could go second distribution, inverse normal. The area wouldn't be 0.95, it would be 2.5%, or 0.025. And then the mu would still be 0, the sigma would still be 1, and we're doing a left tail. those older calculators don't even have these options for left, center, or right. It just assumes a left tail. Then you click paste, hit enter, and it tells me negative 1.96. Now, even though it tells you negative 1.96, the z sub c that you want for this formula up here is just the positive value, or the absolute value of whatever you find. So it's just positive 1.96 is that z sub c value. All right, and then sigma, it tells me, is 7.9, so that's what sigma is, and n is however many we had in our sample. So I got to remember how many were in that sample. So let me go back a page and count how many were in the sample. I got to go back one more page. Okay. How many are in here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 columns, and 1, 2, 3, 4 rows. So that's 40 in my sample. I'll go back to my other page now. So n is 40. So then I go to my calculator and I say 1.96. Usually you want to do probably 4 decimal places, but since this is 996, it's going to round those up, nines up to zeros anyway. So 1.96. That's the z sub c times the sigma, which it told me was 7.9, and then where's the 9? And then divided by the square root of 40. And so my margin of error is 2.448 or 2.45. All right. 2.448. So that's my margin of error. So our interpretation is you are 95% confident that the margin of error for the population mean is about 2.4 hours. So the margin of error is about 2.4 hours based on the 95% confidence level and based on the sample size of 40 in my sample, and based on the population standard deviation being known to be 7.9 hours. That finds my margin of error. Now, that doesn't construct the confidence interval yet. The confidence interval is actually going to be the mean of my sample plus or minus my margin of error. So let's go ahead and talk about how we would do that. Remember that the mean of that population, the mean of that sample was, I got to remember it, the mean of that sample was 29.6. So I would have to say 29.6 minus 2.4. So 29.6, that was my X bar. That was my sample mean. But to get my confidence interval, I'm going to say 29.6. Remember, my margin of error was 2.4. So I'm going to say 29.6 minus 2.4 and 29.6 plus 2.4. And so that's going to give me, I believe that's going to give me, if I did my arithmetic right, it's going to give me 27.2 on the low end and 32 on the high end. So that means we are 95% confident. 95% confident that the true population mean is somewhere between 27.2 and 32. It means there's a 95% probability that the population mean is between those two values. I think what it means is that whatever the population mean is, that 95% of the samples would fall between those two values. If the population mean were 29.6, then 95% of the samples would fall between those two values, sample means. All right, moving on. That's what this page is going to teach us. The confidence interval is what we have to do is we have to take the sample mean and subtract the margin of error and take the sample mean and add the margin of error and say that mu is somewhere between those two final values, a low value and the high value, with some sort of percent of confidence. Okay, you can read these guidelines if you want to. Pause it and read those guidelines, see if it makes it make more sense to you. All right, so as we just said earlier, this is what we did, what I just showed you. This is example 3, but I've already showed you how to do it. You do what we just did to get that confidence interval. All right. You can also, now there's actually a much easier way to do it. You'll be glad to hear. There's an even easier way to do it in your calculator than what we just did. The calculator will just construct the confidence interval for you. Use the data in example 1 in technology to construct a 99% confidence interval for the mean number of hours worked by grocery store employees. Here is the ultimately easiest way to do this. Besides the way we just showed you how to do it. That's kind of a more thoroughly detailed way of how to do it, but the calculator will do all that for you. You just go to stat, and click over to tests. And we're going to choose option 7, Z interval. You use option 7, Z interval, when the population standard deviation is known. So everything is 6.1 is going to be using the Z interval. Option 8, the T interval, is going to be 6.2 when the population standard deviation is unknown. So for now, we are using the Z interval, option 7. You have two ways to do this. One way is to use the data that you already typed in. So if we already typed that data into L1, which I haven't done, but if we had, we could just click data. If we don't have all those data, but let's say maybe a problem doesn't give us all those data points, but it just went ahead and gave us all the stats. It says the mean of a sample is this and the standard deviation of population is that. Then you can just go to stats instead of data. If you go to stats, it lets you put in the standard deviation and the mean. So the standard deviation, remember, it told us was 7.9. Well, is this a different one or is this the same? Yeah, construct a 99% confidence interval based on the data we already did. So the population standard deviation was 7.9. The X bar was, I got to remember what it was again. It was 29.6. Again, if we had the data in there, it would just automatically do this. We wouldn't have to even type that stuff in. It would calculate all that for us anyway. The N is the sample size. The sample size is 40. And the level of confidence is not 0.95 this time. It said 99% confidence interval, so it's 0.99. So we just type the confidence level right there and calculate it. And it tells us the interval. If we want to be 99% confident about our interval, then it's going to spread that interval out a little more. Remember, it was 27.2 and it was 32. Well, now it's 26.383 and 32.817. So our interval had to grow a little bit for us to have a higher level of confidence that the true population mean is in that interval. But that's a much easier way to do it. In fact, if you could even do that first, if the question says calculate the margin of error necessary for this confidence interval, I could actually do it this way and just find the margin of error by subtracting either one of these values of this interval from the mean. So I could just say 29.6 minus 26.383, and that would give me the margin of error. Or I could say 32.817 minus 29.6, and that would give me the margin of error. Or you could even do it one third way. You could say 32.817 minus 26.383, and then take that result and divide it in half, divide it by 2, and that would also give you the same margin of error. So that's another way to find the margin of error, besides that formula that I showed you how to do earlier in the video. So if that's something you feel more whatever you feel more comfortable doing, go for it. As far as I'm concerned, in finding the margin of error and finding the confidence interval. So here's the interpretation. With 99% confidence, you can say that the population mean number of hours worked is between 26.4 and 32.8. In examples 3 and 4 and the same sample data were used to construct confidence intervals with different levels of confidence. Notice that as the level of confidence increases, the width of the confidence interval also increases. In other words, when the same sample data are used, the greater the level of confidence, the wider the interval. That's something I've been trying to stress more than once in this video. All right. For a normally distributed population with sigma known, you may use the normal sampling distribution for any sample size as shown in this next example 5. A college admissions director wishes to estimate the mean age of all students currently enrolled. In a random sample of 20 students, the mean age is found to be 22.9 years. From past studies, the standard deviation is known to be 1.5 years and the population is normally distributed. Construct a 90% confidence interval of the population mean age. Okay, so we don't have more than 30 in our sample, but since the population is known to be normally distributed, it doesn't matter about it if our sample size is more than 30. Okay, again, I wouldn't go through all of this that maybe they're going to tell you that you have to do. I would go straight to my calculator. All right, I got to remember these values. The mean is 22.9. I probably won't remember those anyway. But let me just go to my calculator. I would go second. No, I wouldn't. I would just go stat. Click over to tests. Z interval, option 7. I don't have data this time. I just have the stats from the data given to me in the problem. The sigma, it says, was known to be 1.5. The mean of the standard deviation, I can't even remember, and I just said it, was 22.9. That was the mean of the sample. The sample size was 20, it told me. And what confidence level does it want? 90% confident. That's going to make my confidence interval be more precise, less wide. It's going to make it come in a lot more when I don't have as much confidence, a higher confidence level. So my confidence interval is 22.348 to 23.452. I'm 90% confident that the mean of the population is between 22.348 and 23.452 based on all the information given. After constructing a confidence interval, it is important that you interpret the results correctly. Consider the 90% confidence interval constructed in example 5. Because mu is a fixed value predetermined by the population, it is either in the interval or not. It is not correct to say there's a 90% probability that the actual mean will be in the interval. So if I said that earlier, then I guess I was a little bit off in saying that. But this statement is wrong because it suggests that the value of mu can vary, which is not true. The correct way to interpret this confidence interval is to say this. Okay, so just get this language, get used to this kind of language. With 90% confidence, the mean is in the interval 22.3 and 23 to 23.5. So I know that's kind of a technicality, but let's just get used to it. This means that when a large number of samples is collected and a confidence interval is created for each sample, approximately 90% of these intervals will contain mu. All right. This correct interpretation refers to the success rate of the process being used, not a probability. Okay, so I know that to me that seems very trivial, but it's probably because I don't have a PhD in statistics. So let's get used to saying it right. Let's just say it with that kind of a language that they want us to use here. All right, moving on. Sample size. For the same sample statistics, as the level of confidence increases, the confidence interval widens. As the confidence interval widens, the precision of the estimate decreases. One way to improve the precision of an estimate without decreasing the level of confidence is simply to increase the sample size. But how large a sample size is needed to guarantee a certain level of confidence for a given margin of error? By using the formula for the margin of error. So we have to find the margin of error. either using this formula, as I showed you earlier in the video, or by constructing the confidence interval and then subtracting either end of the confidence interval from the mean to find. You can do that too to find the margin of error. So if you like that better, do that. A formula can be derived to then find the minimum sample size n, as shown in the next definition. So given a C confidence level and a margin of error E, the minimum sample size needed to estimate the population mean mu is this. So all they did was they did some algebra on this to solve this algebraic equation for n. So you get from here to here by doing some algebra and getting n by itself. When sigma is unknown, you can estimate it using S. S being the standard deviation of your sample, provided you have a preliminary sample with at least 30 members. So if we don't know the population standard deviation, we can use the population, if we don't know the population standard deviation, we can use the standard deviation of our sample to estimate the population standard deviation to use this technique. Determining minimum sample size. The economics researcher in example 1 wants to estimate the mean number of hours worked by all grocery store employees in the county. How many employees must be included in the sample to be 95% confident that the sample mean is within 1.5 hours of the population mean? So it gives us the standard error that we want here. The standard error that we want is 1.5 hours, right? Confident that the sample mean is within 1.5 hours. That means that's our standard error. All right, so we just use this formula up here. All right, 1.95 goes in for E. Z sub C is what we found before, as I showed you how to find it before. Again, we find that Z sub C by, you can rewind the video to what we did earlier, but you go second, second distributions. Oh, I got to quit what I'm doing first. Second quit to get out of that. Second quit. Go to second distributions, inverse normal. And if we want to be 95% certain, 95% confidence interval, you can either do this left tail method or do the center method if you have that capability on your calculator. Do 0.95 right here, and that'll give you your Z sub C. And the sigma is something that they gave us earlier, was 7.9. And then we just plug it in that formula and we can get our sample size that we need, which is in this case 106.56. So we need at least 107 subjects in our sample. We can get more than that, but we need at least 107 to have that kind of confidence and margin of error. And that is the end of section 6.1. Good luck on that assignment. I'll see you again in 6.2.